Let's start with something simple. Right now, somewhere out in the universe, there is a black hole dying. Not collapsing, not being destroyed by some cosmic collision, but quietly, almost imperceptibly, fading away, losing itself one tiny particle at a time, radiating the faintest possible glow into the emptiness around it. And eventually, not soon, not in any time frame that means anything to a human life, but eventually, it will be gone. Everything it ever swallowed, every star it consumed, every photon of light that crossed its boundary and vanished from view, all of that will have been converted into the thinnest, most diffuse haze of radiation imaginable. And then nothing. Just empty space where something impossibly dense and impossibly strange used to be. That's what we're going to talk about tonight. How the most permanent-seeming objects in the universe, things so powerful that not even light can escape them, are slowly, inevitably disappearing. And what that means for, well, everything. For matter, for information, for the universe itself. Because it turns out that the disappearance of black holes isn't just a curiosity. It's one of the deepest puzzles in all of physics, a problem that sits right at the intersection of gravity and quantum mechanics, the two pillars that hold up our understanding of reality. And the fact that we still don't fully understand what happens when a black hole evaporates tells us something profound about the limits of what we know. But let's not get ahead of ourselves. Let's start at the beginning. Or rather, let's start with what you probably already know about black holes, and then see how far we can go from there. You've heard the basic idea. A black hole is a region of space where gravity is so intense that nothing can escape. Not matter, not radiation, not light. Once something crosses a certain boundary, the event horizon, it's gone, pulled inward toward a point of infinite density, a singularity, where the laws of physics as we understand them simply stop working. It's the ultimate one-way door. Things go in, nothing comes out. And that picture, as far as it goes, is basically correct. It's what Einstein's general theory of relativity predicts, and it's been confirmed by observation after observation. We've seen stars orbiting invisible companions that can only be black holes. We've detected gravitational waves from black holes merging. We've even taken a picture of one, or rather, a picture of the shadow one casts against the glowing material swirling around it. The image from the Event Horizon Telescope in 2019, that orange ring of fire around a dark circle, that was the supermassive black hole at the center of the galaxy M87, a monster containing the mass of 6.5 billion suns. Black holes are real. They're out there, and they do exactly what the theory says they should do. But here's the thing. That picture, the one where black holes are perfect, permanent, inescapable traps, is incomplete. It's the classical picture, the one you get from general relativity alone. And general relativity, magnificent as it is, doesn't know about quantum mechanics. It doesn't account for the weird, probabilistic, deeply strange behavior of matter and energy at the smallest scales. And when you add quantum mechanics to the story, something remarkable happens. Black holes start to glow. Not brightly. We're talking about a glow so faint that no instrument we've ever built could detect it from even the nearest black hole. But it's there, in principle. A black hole, it turns out, is not perfectly black. It radiates. It has a temperature. And because it has a temperature, it slowly loses energy. And because energy and mass are the same thing, that's what Einstein's famous equation E equals mc squared tells us. Losing energy means losing mass. A black hole that radiates is a black hole that's shrinking, and a black hole that's shrinking is a black hole that will, given enough time, evaporate completely. This idea, that black holes radiate and eventually vanish, is one of the most extraordinary predictions in the history of physics. It was made in 1974 by Stephen Hawking, and it changed everything. Not because it meant black holes would disappear tomorrow, or next century, or even in the entire remaining lifetime of the universe as we know it. The timescales involved are staggeringly, incomprehensibly long. A black hole with the mass of our sun would take something like 10 to the 67th years to evaporate. That's a 1 with 67 zeros after it. The current age of the universe is about 14 billion years, which is roughly 10 to the 10th. So we're talking about a timescale that's not just longer than the age of the universe. It's longer by a factor that makes the age of the universe look like the blink of an eye. For a supermassive black hole, the kind at the center of a galaxy, the evaporation time is even more absurd, something like 10 to the 100th years. A Google years. A number so large it barely qualifies as a number in any meaningful sense. So no, black holes are not disappearing in any way you'd notice. Not now. Not for an unimaginably long time. But the fact that they will, eventually, disappear, that's what matters. Because it raises questions that cut to the very heart of physics. Questions about what happens to information when it falls into a black hole. Questions about whether the laws of quantum mechanics, laws that are supposed to be inviolable, that underpin every other piece of physics we've ever tested, can survive the encounter with gravity at its most extreme. Questions about the fundamental nature of space, time, and reality itself. And those questions are still open. Right now, as you're lying there, some of the smartest people on the planet are working on them. And they don't have the answers yet. Not completely. Not in a way that everyone agrees on. And that, honestly, is part of what makes this so fascinating. We're at the edge of knowledge, looking over into something we don't yet understand. So let's walk to that edge together. Let's start with how we got here. The story of black holes begins, like so many stories in modern physics, with Albert Einstein. In 1915, Einstein published his general theory of relativity, which reimagined gravity not as a force pulling objects together, Newton's picture, but as a consequence of the curvature of spacetime. Mass and energy, Einstein showed, warp the fabric of space and time around them, and objects moving through that warped spacetime follow curved paths, paths that look, to us, like the effect of a gravitational force. The Earth doesn't orbit the Sun because the Sun is pulling it. The Earth orbits the Sun because the Sun's mass has curved spacetime in such a way that the Earth's natural path through space loops around and around. This was a revolutionary idea, and it came with a set of equations, Einstein's field equations, that describe exactly how mass and energy curve spacetime. These equations are beautiful, powerful, and notoriously difficult to solve. Einstein himself could only find approximate solutions for simple cases, but within months of the theory being published, while serving on the Eastern Front during World War I, a German physicist and astronomer named Karl Schwarzschild found an exact solution. Schwarzschild's solution described the spacetime around a perfectly spherical, non-rotating mass, and it contained a surprise. At a certain distance from the center of the mass, a distance that depended only on how much mass there was, something strange happened to the equations. The mathematics produced what's called a singularity, a point where quantities blow up to infinity. At this distance, which we now call the Schwarzschild radius, time appeared to slow to a halt for an outside observer, and space seemed to become infinitely stretched. And at the very center, at the point where all the mass was concentrated, there was another singularity, a point of genuinely infinite density, where the curvature of space-time became infinite. Now, Schwarzschild himself didn't immediately realize what this meant. Neither did Einstein. In fact, Einstein spent much of the rest of his life convinced that these mathematical singularities were artifacts, quirks of the mathematics that wouldn't correspond to anything real. The idea that a real physical object could collapse to a point of infinite density, surrounded by a surface from which nothing could escape, seemed absurd. Surely nature wouldn't allow such a thing. But nature, it turns out, doesn't care what seems absurd to us. The person who first took the idea seriously, who first showed that gravitational collapse to a singularity wasn't just a mathematical curiosity, but a genuine physical possibility, was a young Indian physicist named Subramanian Chandrasekhar. In 1930, at the age of just 19, while on a steamship voyage from India to England to begin graduate study at Cambridge, Chandrasekhar worked out what happens to a massive star when it runs out of fuel. You see, stars spend their lives in a state of balance. The outward pressure from the nuclear fusion happening in their cores pushes against the inward pull of their own gravity. As long as the fusion keeps going, the star holds itself up. But fusion can't last forever. Eventually, the fuel runs out, and when it does, the star has to find some other way to support itself against gravity, or it collapses. For stars like our Sun, the answer is electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. When the Sun exhausts its fuel, it will shrink down to a white dwarf, a dense ball about the size of Earth, but with the mass of a star, held up by the stubborn refusal of electrons to occupy the same quantum state. And there it will sit, cooling slowly, for billions and billions of years. But Chandrasekhar realized there was a limit. If the star was too massive, more than about 1.4 times the mass of the Sun, electron degeneracy pressure wouldn't be enough. The gravity would be too strong. The electrons would be forced into the protons, creating neutrons, and the star would collapse further, past the white dwarf stage, into something even denser. This limit, 1.4 solar masses, is now called the Chandrasekhar limit, and it earned him the Nobel Prize in Physics in 1983. But at the time, his result was met with hostility. Arthur Eddington, one of the most prominent astrophysicists of the era, and the man who had confirmed Einstein's general relativity by observing the bending of starlight during a solar eclipse, publicly ridiculed Chandrasekhar's work. Eddington simply couldn't accept that a star could collapse without limit. There should be a law of nature to prevent a star from behaving in this absurd way, he declared. But there wasn't, and Chandrasekhar was right. It took decades for the physics community to fully work out what happens when a star collapses beyond the Chandrasekhar limit. In the 1930s, Fritz Zwicky and Walter Baade proposed the existence of neutron stars, objects so dense that a teaspoon of their material would weigh about 1 billion tons. These are stars that have been squeezed so hard that their atoms have been crushed, their electrons forced into their protons, creating a ball of neutrons just 10 or 12 miles across, but containing more mass than the Sun. Neutron stars are held up by neutron degeneracy pressure, another quantum mechanical effect, similar to the one that holds up white dwarfs but operating at much higher densities. And neutron stars are real. We've observed them. They spin rapidly, some of them hundreds of times per second, and they emit beams of radiation from their magnetic poles that sweep across the sky like cosmic lighthouses. We call those pulsars. The first one was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge, who noticed a regular, repeating radio signal coming from a fixed point in the sky. The signal was so precise, so clock-like, that her supervisor initially half-jokingly labeled it LGM-1 for Little Green Men. It wasn't aliens, of course. It was a neutron star, spinning and beaming, a collapsed stellar core with a density beyond imagination. But here's the thing about neutron stars. They, too, have a limit. If the original star is massive enough, roughly more than about 2 to 3 solar masses of material remaining after the supernova explosion, then not even neutron degeneracy pressure can hold it up. Nothing can. No known force in the universe is strong enough to resist the inward crush of gravity at that point. And so the collapse continues, past the neutron star stage, past anything recognizable. The matter falls inward, and the curvature of space-time around it grows steeper and steeper, until eventually, the escaping velocity, the speed you'd need to reach to fly away from the surface, exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. A black hole is born. The boundary, where the escape velocity equals the speed of light, is the event horizon. And it's important to understand what the event horizon is and what it isn't. It's not a physical surface. If you were falling into a black hole, a big enough one, you wouldn't feel anything special as you crossed the event horizon. There's no wall, no barrier, no sudden change in the laws of physics at that point. Space-time is smooth there. You'd just keep falling, but you would have crossed an invisible line, past which your return becomes impossible. No matter how hard you tried to fly back out, no matter how powerful your rocket engines, the curvature of space-time beyond the event horizon is such that all paths, every possible trajectory through space, lead inward, toward the singularity. The future, in a very real and mathematical sense, points inward. Escaping a black hole once you're inside the event horizon isn't just difficult. It's not a matter of having a fast enough engine. It's more fundamental than that. Trying to escape a black hole from inside the event horizon is like trying to travel backward in time. The geometry of space-time simply doesn't allow it. Now, the term black hole itself didn't come along until much later. For years, these objects were called frozen stars, or gravitationally completely collapsed objects. Not exactly catchy. The name black hole was popularized by the American physicist John Archibald Wheeler in 1967 during a lecture at NASA's Goddard Institute for Space Studies. Wheeler was one of the towering figures of 20th century physics. He'd worked on the Manhattan Project. He'd coined the terms wormhole and quantum foam, and he had a gift for vivid, memorable language. Black hole, stuck immediately. It captured something essential about these objects. The darkness, the finality, the sense of something swallowing everything around it and giving nothing back. And that idea, that black holes give nothing back, was the accepted wisdom for decades. A black hole was the ultimate endpoint. Matter falls in, information falls in, and neither ever comes out again. The event horizon was a perfect one-way membrane. What happens inside the black hole stays inside the black hole forever, until Stephen Hawking came along and showed that forever might not be as long as everyone thought. To understand what Hawking discovered, we need to take a detour into the quantum world, and this is where things get genuinely strange. Because the quantum world is strange. Not strange in a poetic, metaphorical way. Strange in a way that bothers physicists. Strange in a way that, after 100 years of working with quantum mechanics, some of the deepest minds in physics still argue about what it actually means. But let's start with something specific. Let's talk about the vacuum, empty space, nothing. Except in quantum mechanics, nothing is never really nothing. You see, one of the fundamental principles of quantum mechanics is the Heisenberg uncertainty principle, which says that certain pairs of physical quantities, like position and momentum, or energy and time, can't both be precisely known at the same time. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our instruments or our cleverness. It's a fundamental feature of reality. The universe itself doesn't have precise, simultaneous values for these paired quantities. And this has a wild consequence for empty space. Because if you try to pin down the energy of a region of space at a precise moment in time, the uncertainty principle says you can't. There's always a minimum amount of fuzziness, a minimum amount of energy fluctuation that you can't get rid of. Even in a perfect vacuum, even at absolute zero temperature, the quantum fields that fill all of space are constantly fluctuating. Particles and their antiparticles are popping into existence in pairs, borrowing energy from the vacuum, and then annihilating each other and giving that energy back, all in incredibly tiny fractions of a second. We call these virtual particles, and they're a direct consequence of quantum field theory. Now, virtual particles are a tricky concept. They're not quite the same as real particles. You can't detect a single virtual particle with a detector in the way you can detect a real photon or a real electron. They exist, in a sense, below the threshold of direct observation, flickering in and out of existence on timescales so short that the uncertainty principle protects them from violating the conservation of energy. They borrow energy, exist for a fleeting moment, and then pay it back. As long as they do it fast enough, the universe doesn't notice. Or more precisely, the equations allow it. But virtual particles have real, measurable effects. The most famous is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948. If you place two uncharged metal plates very close together in a vacuum, we're talking a distance of a few micrometers, you'll find that they experience a tiny but measurable attractive force pushing them together. The reason is that the plates restrict which virtual particles can exist between them. Only virtual photons, with wavelengths that fit neatly between the plates, can appear in that gap. But outside the plates, virtual photons of all wavelengths can exist. So there are more virtual particles pushing on the plates from outside than from between them, and the plates get pushed together. This has been experimentally confirmed. Virtual particles, even though you can't catch one in your hand, leave fingerprints on the real world. So the vacuum is alive. It's seething with activity, a frothing sea of particles flashing in and out of existence. And this is true everywhere in the universe, including right at the edge of a black hole's event horizon. And that's where Hawking's insight comes in. In 1974, Stephen Hawking was working on the quantum properties of black holes. He'd already done important work on black hole mechanics, showing, for instance, that the area of a black hole's event horizon can never decrease, which is eerily similar to the second law of thermodynamics, which says that entropy, the measure of disorder in a system, can never decrease. That similarity wasn't lost on anyone, but most physicists at the time thought it was just an analogy, a mathematical coincidence, not a deep physical connection. But then Hawking did a calculation that changed everything. He applied quantum field theory, the mathematical framework that describes quantum fields and their fluctuations, to the curved spacetime around a black hole. And what he found astonished him. It astonished everyone. Here's the picture, simplified but essentially correct. Imagine those virtual particle pairs popping in and out of existence near the event horizon of a black hole. Normally, A particle and its antiparticle appear, exist for a fleeting moment, and then annihilate each other. But near the event horizon, something different can happen. Sometimes, one of the pair gets caught by the black hole's gravity and falls across the event horizon, while the other escapes into the space outside. The particle that escapes carries real energy away from the black hole. It becomes a real particle, no longer virtual, but actual, detectable radiation streaming away from the event horizon. Now, energy has to be conserved. The escaping particle carries positive energy, so the particle that fell in must have carried negative energy, a concept that sounds bizarre, but makes sense in the extreme gravitational environment near a black hole. That negative energy reduces the total energy, and therefore the total mass, of the black hole. The black hole has lost a tiny amount of mass. It has, in effect, radiated. This is Hawking radiation, and the remarkable thing about it is that it has a thermal spectrum, the same kind of spectrum you'd expect from a perfectly glowing object at a specific temperature. The black hole has a temperature. It's radiating like a black body, just as a hot stove radiates infrared light or a glowing ember radiates visible light. Except the black hole's temperature is astonishingly low. For a black hole with the mass of our Sun, the Hawking temperature would be about 60 billionths of a Kelvin above absolute zero. That's 60 nanokelvin. Colder than anything that has ever existed naturally in the universe. Colder than the cosmic microwave background radiation, which fills all of space at a temperature of about 2.7 Kelvin. So a solar mass black hole is actually absorbing more energy from the cosmic microwave background than it's radiating through Hawking radiation. It's gaining mass, not losing it, for now. But give it time. A lot of time. Eventually, the universe will expand and cool to the point where the cosmic microwave background temperature drops below the Hawking temperature of the black hole. And when that happens, the black hole will start losing more energy than it gains. It will begin to shrink. Slowly at first, incredibly, fantastically slowly. But the shrinking accelerates. Here's why. The temperature of a black hole is inversely proportional to its mass. The more massive the black hole, the cooler it is. The less massive, the hotter. Think about what that means. As a black hole radiates and loses mass, it gets hotter. And because it's hotter, it radiates more intensely. And because it radiates more intensely, it loses mass faster, which makes it even hotter, which makes it radiate even more. It's a runaway process, a feedback loop that accelerates the black hole's demise. For most of a black hole's life, this process is so slow as to be completely negligible. A stellar mass black hole, one with maybe 10 times the mass of the Sun, would take something like 10 to the 68th years to evaporate. To put that in perspective, the universe is currently about 1.4 times 10 to the 10th years old. So the evaporation time is roughly 10 to the 58th times the current age of the universe. That's a number so large that comparisons become meaningless. If the age of the universe were a single grain of sand, the evaporation time would be, well, there aren't enough grains of sand on Earth, or in all the beaches of all the planets in all the galaxies, to represent it. It's an absurdity of time, but the final stages are different. As the black hole shrinks, the process speeds up dramatically. In the last fraction of a second, a black hole that has been placidly evaporating for eons beyond counting suddenly releases an enormous burst of energy. Its temperature spikes to unimaginable levels. The radiation pours out, and then it's gone. The black hole has evaporated completely, leaving behind nothing but a fading cloud of particles and radiation spreading out into space. What does that final burst look like? It depends on the mass at the end, but Hawking's calculations suggest that the last moments of a black hole's life would release energy equivalent to a very large nuclear explosion. Around 1,000,000 megaton nuclear explosion happening in a fraction of a second. Not nearly enough to threaten anything at astronomical distances, but certainly a remarkable fireworks display by any terrestrial standard. Astronomers have actually looked for these events, scanning the sky for the characteristic gamma-ray bursts that might signal the final evaporation of a tiny black hole. So far, they haven't found any, which either means there aren't many small black holes nearby, or that something about the final stages of evaporation is different from what we predict. Both possibilities are interesting. Now, let's sit with this for a second. What Hawking showed is that black holes, objects defined by their ability to trap everything, to let nothing escape, actually do let something escape. They radiate, they have a temperature, they shrink, and they eventually vanish. This turns the very definition of a black hole on its head. The event horizon, that supposedly perfect one-way membrane, turns out to be slightly leaky. Not leaky in the sense that something comes back out from inside. Nothing crosses the event horizon in the outward direction. The radiation comes from just outside the horizon, from the quantum fluctuations of the vacuum in the extreme gravitational field. But the effect is the same. The black hole loses mass. The prison has a slow leak. And this realization, that black holes radiate and evaporate, immediately raised a question that has haunted physics ever since. A question so profound, so troubling, that it sparked what the physicist Leonard Susskind called the Black Hole War, a decades-long intellectual battle involving some of the greatest minds in theoretical physics. The question is this: what happens to the information? To understand why this is such a big deal, we need to talk about what physicists mean by information and why its preservation is so important. In everyday life, information is stuff like the words on a page, the data on a hard drive, the arrangement of your furniture in your living room. But in physics, information has a more fundamental meaning. The information content of a physical system is a complete description of that system's quantum state. Everything you would need to know to fully specify what the system is and how it will evolve over time. The positions, momenta, spins, charges, and quantum correlations of every particle in the system. And here's the crucial point. According to the laws of quantum mechanics, information is never destroyed. It can be scrambled, rearranged, spread out, made practically impossible to recover, but it's always there, in principle. This is a property called unitarity, and it's one of the bedrock principles of quantum mechanics. The time evolution of a quantum system is described by a unitary operator, which is a fancy way of saying it's reversible. Given the final state of a system, you could, in principle, with perfect knowledge, reconstruct the initial state. Nothing is lost. The universe keeps perfect books. Think of it this way. Imagine you have a book, a novel, say. You throw it into a fire. The book burns. Its pages curl and blacken. Its ink vaporizes. Eventually, all you have left is ash, smoke, and heat. The book is gone, right? Well, no. Not from the perspective of fundamental physics. In principle, if you could track every single molecule of ash, every particle of smoke, every photon of heat radiation that the fire emitted, you could, theoretically, reconstruct the entire book. Every word, every page. The information isn't gone. It's just been scattered into an incredibly complex, incredibly diffuse form. Practically impossible to recover, sure, but not fundamentally destroyed. This is not just a thought experiment. It's a fundamental law. And it has been tested and confirmed in every area of physics where we've been able to check it. Information conservation is one of those principles that physicists will go to enormous lengths to defend, because the consequences of abandoning it are severe. If information can be destroyed, the whole mathematical framework of quantum mechanics, the most precisely tested theory in the history of science, comes apart. Now, here's where black holes cause a problem, a big one. Imagine you throw that same book into a black hole instead of a fire. The book crosses the event horizon and falls toward the singularity. The information about the book, the arrangement of atoms that encoded the words, the sentences, the story, is now inside the black hole. But remember, the black hole is evaporating. Hawking radiation is carrying energy away from the event horizon. And here's the critical question. Does the Hawking radiation carry the information with it? Hawking's original calculation said no. The radiation, he showed, is perfectly thermal, random, featureless heat radiation that carries no information about what fell into the black hole. It's like the glow from a hot poker. The radiation tells you the temperature of the poker, but it doesn't tell you whether the poker was used to stir a fire or hang on a wall or do anything else. The Hawking radiation tells you the mass, charge, and angular momentum of the black hole, but nothing else. Nothing about the book. Nothing about the star that collapsed to form the black hole. Nothing about anything that ever fell in. And this means that when the black hole finally evaporates completely, when all that's left is a diffuse cloud of featureless thermal radiation, the information about the book is gone. Not scrambled, not rearranged, not hidden. Gone. Destroyed. Erased from the universe. If that's true, it violates the unitarity of quantum mechanics. The information was there before the black hole evaporated, and it's not there after. The universe's books don't balance. Quantum mechanics says this can't happen. But Hawking's calculation, which uses the well-established framework of quantum field theory and curved spacetime, says it does. This is the black hole information paradox, and it has been called, without exaggeration, the most important problem in theoretical physics. Hawking himself was initially quite comfortable with the conclusion. He argued, essentially, that gravity wins, that the extreme conditions near and inside a black hole represent a situation so unlike anything quantum mechanics was designed to handle that the usual rules don't apply. Information destruction, he said, is just what happens when you combine quantum mechanics with strong gravity. We need to update our understanding of quantum mechanics to accommodate it. But many other physicists, perhaps most of them, were horrified by this suggestion. They couldn't accept that information could be destroyed because the consequences were too dire. If unitarity fails for black holes, why should we trust it anywhere? The whole structure of quantum mechanics depends on it, and quantum mechanics works. It works spectacularly well. It predicts the outcomes of experiments to 10 decimal places. It explains how atoms are structured, how chemistry works, how transistors function, how lasers emit light. It is, by any measure, the most successful and precisely tested scientific theory ever devised. Throwing away unitarity felt like burning down the house to fix a leaky faucet, and so a war began. Not with weapons, but with papers and arguments and conferences and blackboard calculations. On one side, Hawking, arguing that information is truly lost when black holes evaporate. On the other side, a growing coalition of physicists, led most vocally by Leonard Susskind of Stanford and Gerard Hooft of the University of Utrecht, arguing that information must somehow escape, that Hawking's calculation was missing something, and that unitarity must be preserved. This was a real dispute. Physicists took sides. Bets were placed, literally. In 1997, Hawking and Kip Thorne bet John Preskill, a Caltech physicist, that information is indeed lost in black hole evaporation. The stakes were an encyclopedia of the winner's choice, a tongue-in-cheek acknowledgement that the bet was really about whether information could survive the ultimate shredder. The argument raged for decades, and it touched on some of the deepest ideas in physics. Let me walk you through the main threads, because each one reveals something important about how the universe works. First, let's talk about black hole entropy and the work that led up to Hawking's discovery. Because the story of Hawking radiation actually starts with a graduate student named Jacob Bekenstein, who had a remarkably bold idea. In the early 1970s, Bekenstein was a PhD student working with John Wheeler at Princeton. Wheeler, ever the provocateur, liked to pose paradoxes to his students to make them think. And one of his favorites went like this. What happens if you take a cup of hot tea, a system with high entropy, and pour it into a black hole? Before the tea goes in, the universe has a certain amount of entropy. Entropy is a measure of disorder, of the number of ways a system can be arranged without changing its macroscopic properties. A cup of hot tea has a lot of entropy. The water molecules are bouncing around in all sorts of ways. But once the tea crosses the event horizon, it's gone. The black hole has swallowed it. And according to the classical picture of black holes, the black hole is completely characterized by just three numbers: its mass, its electric charge, and its angular momentum. Nothing else. This is the no-hair theorem, the idea that a black hole has no distinguishing features beyond those three quantities. All the complex, high-entropy information about the tea is lost. The total entropy of the universe outside the black hole has decreased. But wait. The second law of thermodynamics says that entropy can never decrease. It's one of the most robust principles in all of physics. And here we have a situation where it seems to be violated. Just toss things into a black hole, and entropy disappears. Bekenstein's bold idea was that the black hole itself has entropy, lots of it. The entropy of the black hole, he proposed, is proportional to the surface area of its event horizon, not the volume, the surface area. This was a strange and unexpected claim. In every other system in physics, entropy scales with volume. A box of gas has entropy proportional to the number of molecules, which depends on the volume. But for black holes, Bekenstein argued, entropy lives on the surface, the area of the event horizon. When you throw the tea into the black hole's mass increases, because the tea has mass and energy, and its event horizon grows. The increase in the black hole's entropy, Bekenstein proposed, more than compensates for the entropy that was lost when the tea disappeared behind the horizon. The second law is saved. Total entropy, the entropy of everything outside the black hole, plus the entropy of the black hole itself, still increases. This was a remarkable insight. But Bekenstein had a problem. If the black hole has entropy, and entropy is related to temperature, which it is, through the fundamental laws of thermodynamics, then the black hole must have a temperature, and if it has a temperature, it must radiate. But black holes don't radiate. They're black, that's the whole point. At least, that's what everyone thought at the time. Hawking initially set out to prove Bekenstein wrong, to show that black holes couldn't have real thermodynamic properties, that the analogy between black hole mechanics and thermodynamics was just an analogy. And in the process of trying to prove Bekenstein wrong, Hawking proved him right. Black holes do have entropy, they do have a temperature, and they do radiate. Hawking's calculation confirmed Bekenstein's insight and made it precise. The entropy of a black hole is exactly 1/4 of the area of its event horizon, measured in Planck units. And the temperature is inversely proportional to the mass, exactly as you'd need for the thermodynamic relationships to work out. This formula, the Bekenstein-Hawking entropy, is one of the most important equations in theoretical physics, and one of the most mysterious, because it raises a profound question. Why surface area? Why not volume? If the entropy of a black hole is proportional to its surface area, what does that mean about where the information is stored? Is all the information about everything that ever fell into a black hole somehow encoded on its two-dimensional surface? That question would eventually lead to one of the most mind-bending ideas in all of physics, the holographic principle. But we'll get to that. First, let me tell you about the man who fought hardest against Hawking's conclusion that information is destroyed. Leonard Susskind is one of the founders of string theory, a professor at Stanford, and a physicist with an almost combative intellectual personality. He doesn't suffer what he considers to be bad ideas gladly, and he considered Hawking's claim that information is lost to be a very bad idea indeed. Not because he thought Hawking's calculation was wrong. The calculation is beautiful and almost certainly correct, but because he believed Hawking was drawing the wrong conclusion from it. The radiation is thermal, yes, but Susskind argued that there must be subtle correlations in the radiation, patterns so faint and so complex that they look random at first glance, but actually encode the information about everything that fell in, like a message written in invisible ink that only appears when you hold the paper up to a flame. Suskind's analogy was different, but the idea is the same. He compared it to burning a book, the same analogy we used earlier. When you burn a book, the radiation looks random and thermal, but the information isn't destroyed. It's encoded in the incredibly complex correlations between the photons and smoke particles and ash. In principle, you could reconstruct the book from the fire's emissions. Susskind argued that Hawking radiation works the same way. The radiation from an evaporating black hole looks thermal, but the information is hidden in the correlations, in the way that the particles emitted at one time are quantum mechanically entangled with particles emitted at other times. You'd need to collect every single particle of Hawking radiation and perform an impossibly complex quantum computation to decode it. But the information would be there. This sounds reasonable, but there's a problem, and it's a big one. If the information about what falls into a black hole eventually comes out in the Hawking radiation, then at some point during the evaporation process, the information is in two places at once. It's inside the black hole, because nothing has crossed the event horizon outward, and it's also in the radiation, encoded in those subtle correlations. And that's a problem, because quantum mechanics says information can't be in two places at once. There's a fundamental principle called the no-cloning theorem that says you can't make an exact copy of a quantum state. If the information is inside the black hole, it can't also be outside. If it's outside, it can't also be inside. This contradiction is at the heart of the black hole information paradox, and it's why the problem is so hard. Every proposed solution seems to violate some fundamental principle of physics. If information is destroyed, you violate unitarity. If information escapes, you violate the no-cloning theorem. If information stays trapped inside a remnant, some tiny object left behind after the black hole evaporates, you run into other problems, like the fact that a Planck mass remnant would need to store a potentially infinite amount of information, which has its own physical absurdities. It's a genuine impasse. The kind of problem that, when you sit with it long enough, starts to feel like it's telling you something deep about the nature of reality, something that our current theories can't quite articulate. Let's take a breather from the hard stuff for a moment and talk about something you can actually feel. Right now, as you're lying there, gravity is holding you against your bed. Your weight, the pressure you feel against the mattress, is the curvature of space-time, caused by the Earth's mass, gently guiding your body downward. It's the same force, the same fundamental phenomenon that powers black holes. The difference is only one of degree. Here, near the surface of the Earth, the curvature is gentle, almost imperceptible. At the event horizon of a stellar black hole, it's extreme beyond imagining. But it's the same thing, the same geometry, the same physics. The force that holds you softly in bed tonight is the same force that, taken to its extreme, can trap light and swallow stars. And that's part of what makes black holes so captivating. They're not exotic in the sense of being made of some strange, otherworldly substance. They're made of gravity, the same gravity you interact with every moment of your life. Black holes are what happens when gravity is pushed to its absolute limit, when the curvature of space-time becomes so extreme that it folds in on itself. They're gravity, with nowhere left to go. Now, let's get back to the information paradox, because there are some genuinely fascinating ideas about how it might be resolved. And each one, whether right or wrong, illuminates something extraordinary about how the universe works. One of the most influential ideas to come out of the black hole information debate is the holographic principle. Remember how Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. The holographic principle takes this observation and runs with it. It says that everything that happens inside a volume of space, all the particles, all the fields, all the information, can be described by a theory that lives on the boundary of that volume. The three-dimensional reality we experience is, in some deep sense, a projection of information stored on a two-dimensional surface, like a hologram. This sounds like science fiction, but it has solid mathematical backing. The most concrete realization of the holographic principle was provided in 1997 by the Argentine-American physicist Juan Maldacena, then at Harvard. Maldacena showed, in a paper that became one of the most cited in the history of physics, that a specific kind of gravitational theory, in a hypothetical space called anti-de Sitter space, a space with a particular geometric structure, is exactly equivalent to a non-gravitational quantum theory living on the boundary of that space. This correspondence, known as AD-S-CFT, or sometimes just the Maldacena conjecture, provides a concrete example of holography in action. A world with gravity, in the interior of this space, is completely described by a theory without gravity, on the boundary. Why does this matter for black holes? Because in the boundary theory, the non-gravitational quantum theory, there are no black holes. There's just ordinary quantum mechanics, operating in a lower dimensional space, with unitarity fully intact. Information is never destroyed on the boundary. And if the boundary theory is equivalent to the gravitational theory in the interior, then information can't be destroyed in the interior either. Black holes might look like they destroy information from the perspective of someone inside the space, but the boundary theory says that information is always preserved. The holographic dual guarantees it. This was a powerful argument. It didn't tell you exactly how the information gets out of the black hole. The mechanism was still unclear, but it provided strong circumstantial evidence that information is preserved. Unitarity wins. Hawking's conclusion about information destruction must be wrong, even though his calculation of the radiation itself is correct. And in 2004, Hawking conceded. At a conference in Dublin, he publicly admitted that he had been wrong about information loss. Black holes, he now believed, do not destroy information. The information somehow escapes in the Hawking radiation. encoded in those subtle correlations that are practically impossible to decode, but theoretically present. He paid off his bet with John Preskill, presenting him with a baseball encyclopedia, a cheeky symbol of information preserved. Now, Hawking's concession didn't mean the problem was solved. Far from it. Saying information escapes in the Hawking radiation is one thing. Showing exactly how, in detail, is another. And that question, the mechanism by which information escapes, remains one of the most active areas of research in theoretical physics today. But before we get to the latest developments, there's another chapter in this story that we need to cover. Because just when physicists thought they might be making progress, someone came along and made the problem worse. In 2012, a group of physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, published a paper that sent shockwaves through the theoretical physics community. They showed that three seemingly uncontroversial assumptions about black holes are mutually inconsistent. You can't have all three. Something has to give. The three assumptions are: first, unitarity. Information is preserved. Second, the equivalence principle. A freely falling observer crossing the event horizon of a large black hole doesn't experience anything unusual. Third, the validity of quantum field theory in low curvature regions of spacetime. The idea that our standard physics works fine in the region just outside the event horizon, where gravity is strong, but spacetime curvature is still manageable. These three assumptions, which most physicists would have happily accepted individually, can't all be true simultaneously. AMPS showed that if you insist on unitarity and the validity of quantum field theory outside the horizon, then the event horizon can't be the smooth, uneventful place that the equivalence principle says it should be. Instead, a freely falling observer would encounter a wall of high-energy radiation, a firewall, at the event horizon. The gentle crossing that general relativity predicts would be replaced by a violent, fatal encounter. The event horizon would burn you to a crisp. This was shocking. The equivalence principle is one of the cornerstones of general relativity. It says that the effects of gravity are locally indistinguishable from acceleration. A person in a freely falling elevator can't tell, by doing experiments inside the elevator, whether they're falling in a gravitational field or floating in empty space. And this should apply at the event horizon of a large black hole, where the space-time curvature is gentle. An astronaut falling through the event horizon of a supermassive black hole shouldn't feel anything. The gravitational tidal forces would be tiny, and the event horizon itself has no physical structure. No wall, no membrane, nothing to notice. But the AMPS argument says there has to be something there if unitarity is to be preserved. The firewall paradox, as it came to be called, forced physicists to confront an uncomfortable truth. Our current understanding of black holes is deeply incomplete. The fact that three of the most well-established principles of physics can't all be true in the vicinity of a black hole's event horizon means that at least one of them must fail. And each option, giving up unitarity, giving up the equivalence principle, or giving up the standard picture of quantum field theory outside the horizon, is deeply unpalatable. No matter which one you choose, something fundamental about our understanding of physics has to change. This is the situation we're in right now. The black hole information paradox and its firewall-shaped cousin sit at the exact intersection of general relativity and quantum mechanics, the two most successful but deeply incompatible theories in physics. They can't both be right in their current forms. And the behavior of black holes, specifically the process of Hawking radiation and evaporation, is the clearest, sharpest place where the conflict between them manifests. Black holes, in other words, aren't just fascinating astronomical objects. They're clues. They're pointing us toward whatever the next revolution in physics will be. The theory that ultimately resolves the black hole information paradox will, almost certainly, be the theory that unifies general relativity and quantum mechanics, the long-sought theory of quantum gravity. And the fact that we don't have that theory yet is one of the greatest unsolved problems in all of science. Let's slow down for a moment and think about what we've covered so far. We started with the simple idea that black holes are inescapable. Nothing gets out. Then Hawking showed that this isn't quite right. Black holes radiate. They have a temperature. They slowly lose mass. Given enough time, they evaporate completely. And that evaporation raises a devastating question. Where does the information go? The stuff that fell in. The stars, the gas, the light, your hypothetical book. All of it contributed to the black hole's mass. But the radiation that comes out appears to carry no information about any of it. When the black hole is gone, the information seems to be gone too, and that breaks one of the most fundamental rules of quantum mechanics. So where does the information go? Let's explore some of the answers that have been proposed, because each one is a window into a different way of thinking about reality. One possibility, championed by some physicists for a while, was that the information is simply gone, destroyed. The universe doesn't conserve information perfectly, and black holes are the proof. This was Hawking's original position, and while he eventually abandoned it, it's worth understanding why some people took it seriously. The argument goes like this. General relativity allows for singularities, places where space-time curvature becomes infinite and the known laws of physics break down. At a singularity, all bets are off. Maybe information conservation is one of the casualties. Maybe the singularity at the center of a black hole is genuinely a place where information ceases to exist. The trouble with this view, as we discussed, is that it opens a Pandora's box. If information can be destroyed, you can construct thought experiments that lead to violations of energy conservation, faster than light signaling, and other absurdities. The mathematical framework of quantum mechanics is deeply intertwined with information conservation, and pulling that one thread tends to unravel a lot of other things you want to keep. A second possibility is the remnant hypothesis. Maybe the black hole doesn't evaporate completely. Maybe, at the very end of its life, when it has shrunk down to the Planck mass, the smallest meaningful mass in quantum gravity, about 22 micrograms, unimaginably tiny, it stops evaporating and leaves behind a stable remnant. This remnant would be fantastically small, far smaller than an atom, but it would contain all the information that ever fell into the black hole. Problem solved, right? Well, not quite. The issue with remnants is that a single Planck mass object would need to store an effectively unlimited amount of information. Every black hole that ever existed, regardless of how massive it was or how much stuff fell into it, would leave behind a remnant of the same tiny mass, but with vastly different information content. A black hole that ate a galaxy would leave behind the same mass remnant as a black hole that ate a single star. That means you'd need an infinite number of distinct Planck mass particle species, one for each possible interior state. This leads to problems with quantum field theory. Specifically, it creates pair production infinities that would make the vacuum unstable. Most physicists find this unacceptable, though a few still defend the remnant idea. A third possibility is the one that has gained the most traction in recent years. The information comes out in the Hawking radiation, encoded in subtle quantum correlations that are invisible to any straightforward analysis but present in principle. This is the position that Susskind championed, that the AD-CFT correspondence supports, and that Hawking eventually conceded to. But saying the information comes out in the radiation is not the same as explaining how, and the mechanism has been the subject of intense research. One key insight came from a concept called the Page curve, developed by the physicist Don Page in 1993. Page asked a simple but powerful question. If a black hole evaporates by emitting Hawking radiation, and the radiation carries information, then how does the entanglement between the radiation and the black hole change over time? Here's the setup. When a black hole first starts evaporating, the radiation it emits is entangled with the black hole itself. Each particle that flies away is quantum mechanically connected to the particle that fell in. As more radiation is emitted, the total amount of entanglement between the radiation and the black hole increases. The entropy of the radiation, a measure of how much information is hidden in the entanglement, goes up. But at some point, something has to change. Because the black hole is shrinking, its surface area is decreasing, and the Bekenstein-Hawking entropy, which is proportional to the surface area, is going down. There comes a moment, roughly halfway through the evaporation process, when the entropy of the radiation reaches the Bekenstein-Hawking entropy of the remaining black hole. After this point, called the Page time, the entropy of the radiation must start to decrease, because the total entanglement can't exceed the black hole's capacity to store information. This means the Hawking radiation must transition from looking random and thermal in the early stages to gradually revealing more and more information about what fell into the black hole as the evaporation proceeds. The entanglement entropy of the radiation goes up, peaks at the Page time, and then comes back down to zero by the time the black hole has completely evaporated. The curve traced by this entropy, up, peak, down, is the Page curve, and its shape tells you that information is preserved. By the time the evaporation is complete, all the information has been transferred from the black hole to the radiation. The Page curve is what you'd expect if information is preserved. But for decades, nobody could derive it from the actual physics of Hawking radiation. Hawking's calculation predicted that the entropy of the radiation would just keep going up, a monotonically increasing curve, indicating that information is never returned. The Page curve and the Hawking calculation gave different answers, and reconciling them seemed impossible. And then, in 2019, something remarkable happened. Two groups of physicists, working somewhat independently, one led by Jeff Pennington, the other by Ahmed Almheri, Thomas Hartmann, Juan Maldacena, and Edgar Chagoulian, with Netta Engelhardt, found a way to derive the Page curve from gravitational physics. Their approach used a concept called the quantum extremal surface, building on ideas from holography and quantum error correction. The details are technically involved, but the upshot is profound. For the first time, there was a gravitational calculation, not just an argument from the boundary theory, but a calculation done within the gravitational theory itself, that reproduced the Page curve and showed that information is preserved during black hole evaporation. This was widely hailed as one of the most important results in theoretical physics in decades. It didn't solve the information paradox completely. There are still deep questions about the mechanism by which information escapes, about what happens at the singularity, about the nature of the black hole interior. But it provided strong evidence that unitarity survives, that information is preserved, and that the tools to prove it are within reach. And it's worth pausing to appreciate what this means. A question that seemed unanswerable for 45 years. Does information survive black hole evaporation? Is now looking like it has an answer. Yes. The universe keeps its books. Nothing is truly lost. Even the most extreme gravitational environments in the cosmos can't destroy information. They can scramble it beyond any practical hope of recovery, but they can't erase it. That's a remarkable thing to know about the universe you live in. But we're not done yet, because the disappearance of black holes has implications that stretch far beyond the information paradox. It connects to some of the biggest questions about the fate of the universe itself. And those questions are worth exploring, especially on a quiet night like this one, when the scale of things seems somehow easier to contemplate. Let's zoom out, way out. Let's think about the universe on the longest possible timescales. Timescales that make the current age of the universe look like the opening chord of a symphony that will play for an eternity. Right now, the universe is about 13.8 billion years old. Stars are shining, galaxies are forming and evolving. New stars are being born in nebulae, planets are orbiting. Life exists, at least on one planet that we know of. The universe is, by cosmic standards, young and vibrant, but it won't always be this way. Stars burn through their fuel. Our sun, a middle-aged star, will last another 5 billion years or so before it exhausts the hydrogen in its core, swells into a red giant, and then sheds its outer layers to leave behind a white dwarf, a hot, dense ember about the size of Earth. And that white dwarf will slowly cool over trillions of years, eventually becoming a cold, dark object called a black dwarf. No one has ever seen a black dwarf, because the universe isn't old enough for any to have formed yet. They're a prediction for a future so distant that it hasn't happened. Other stars will meet different fates. Massive stars will end in supernovae, leaving behind neutron stars or black holes. Smaller stars will burn for trillions of years. Red dwarfs are so efficient with their fuel that the smallest of them could shine for 10 trillion years or more. But eventually, all of them will run out. Every star in the universe will go dark. The last ember will cool, and the universe will enter what the physicist Freeman Dyson called the degenerate era, a vast, cold, dark expanse populated by the remnants of stars, white dwarfs, neutron stars, black holes, and not much else. But even those remnants won't last forever. Protons, the particles that make up the nuclei of atoms, may not be eternal. Some theories of particle physics, grand unified theories which attempt to unify the electromagnetic, weak, and strong nuclear forces, predict that protons eventually decay, with a half-life of perhaps 10 to the 36th to 10 to the 41st years. This hasn't been confirmed experimentally. The Super Kamiokande detector in Japan has been watching an enormous tank of water for decades, waiting for a proton to decay, and hasn't seen one yet. But if proton decay does occur, it means that all ordinary matter will eventually disintegrate. White dwarfs, neutron stars, planets, rocks, every atom of every element in the periodic table, all of it will slowly dissolve into lighter particles and radiation over timescales that dwarf even the stellar era. And then, in this far, far future, what's left? Black holes. They're the last structures standing. After all the stars have burned out, after all the protons have decayed, after all the matter in the universe has been broken down into its lightest possible constituents and scattered across an ever-expanding void, the black holes remain. They're the most durable objects in the cosmos. Supermassive black holes, sitting at the centers of dead galaxies, will persist long after everything else has crumbled. But they, too, are disappearing. Slowly, imperceptibly, one Hawking photon at a time. And eventually, in 10 to the 67th years for a stellar black hole, in 10 to the 100th years or more for the supermassive giants, they'll be gone too. The last black holes will evaporate in a final burst of radiation, and then the universe will contain nothing but a thin, cooling soup of photons, neutrinos, electrons, and positrons, all spreading farther and farther apart as space continues to expand. This is the heat death of the universe, the state of maximum entropy, the end of all thermodynamic activity. No structures, no gradients, no temperature differences, no flow of energy from hot to cold, just an infinite, uniform, featureless void, getting colder and emptier and darker forever. Or at least for so long that forever is the only word that applies. And in this picture, the evaporation of black holes is the final chapter. The last interesting thing that happens in the universe, the last transformation, the last release of energy, the last time the laws of physics produce anything that could be called an event. After the last black hole evaporates, the universe doesn't end. It just stops doing anything. It becomes eternal and empty, a static ocean of particles too spread out to ever find each other again. Think about that for a moment. Every black hole that has ever existed, every one that formed from a collapsing star, every one that grew by swallowing gas and dust and other black holes, all of them are temporary. On a long enough time scale, nothing in the universe is permanent. Not stars, not galaxies, not even the seemingly indestructible gravitational monsters at the hearts of galaxies. Everything fades, everything evaporates, everything is returned, eventually, to the faintest possible form of existence. And all of this grand arc from the birth of the universe to its final, silent emptiness, is connected by that one insight Hawking had in 1974. Black holes radiate. They have a temperature. They are not eternal. They are, like everything else, subject to the quiet, patient workings of thermodynamics. And thermodynamics always wins. There's something almost peaceful about that, isn't there? The idea that even the most extreme, most violent, most gravitationally powerful objects in the cosmos are not immune to the gentle passage of time, that the same basic principles that govern the cooling of your coffee and the fading of a sunset also govern the lives and deaths of black holes. The universe, at its most fundamental level, plays by one set of rules. And those rules say, nothing lasts forever. Everything radiates. Everything comes into balance. Everything returns to equilibrium. But here's the thing, and this is where it gets beautiful again, where the wonder circles back and deepens. If information is preserved during black hole evaporation, if the page curve is correct, and the recent calculations are on the right track, then the story doesn't end with featureless radiation spreading into the void. The radiation that the black hole emits isn't just random thermal noise. It carries, encoded in its quantum correlations, a complete record of everything the black hole ever consumed. Every star, every planet, every photon of light. The information is scrambled beyond any practical hope of reconstruction, but it's there. It's real. It exists, spread out across the cosmos in the faintest possible form, but not destroyed. The universe remembers, even as it fades into darkness, even as the last black holes evaporate and the final photons redshift into oblivion. The information about everything that ever happened is still, in principle, present. Nothing is truly erased. The laws of physics, at their deepest level, are reversible. The universe is a perfect accountant. Every event, every interaction, every moment leaves an indelible mark on the quantum state of the cosmos. And that's not just a poetic sentiment. It's a physical fact, or at least that's what our best current theories say. The unitarity of quantum mechanics, preserved through the most extreme gravitational environments in the universe, means that the history of the cosmos is never lost. It's encoded, permanently, in the quantum correlations between particles that may be separated by billions of light-years and will never interact again. But the record exists. The universe carries its entire history with it, always. Now, I want to come back to something we touched on earlier and explore it more deeply. The connection between entropy and the surface area of a black hole. Because this is one of those ideas that seems technical at first, but, when you really think about it, is genuinely mind-altering. Remember, Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not the volume. This is wildly different from what we'd expect. If you have a box full of gas, the entropy depends on the number of molecules, which depends on the volume. But for a black hole, the entropy scales with surface area, and the numbers are staggering. The Bekenstein-Hawking formula says, entropy is 1/4 of the area measured in Planck units. A Planck area is about 10 to the minus 66 square centimeters. So even a modest black hole has enormous entropy. A solar mass black hole clocks in at about 10 to the 77. If the maximum entropy inside a region of space scales with area rather than volume, perhaps this is telling us something fundamental about the nature of space itself. Perhaps the true degrees of freedom don't fill three-dimensional space the way we imagine. Perhaps they live on surfaces. This is the holographic principle, and it's one of the most radical proposals in physics. The idea, loosely stated, is that everything happening inside a volume of space can be fully described by information on its boundary. The three-dimensional reality we experience might be, in some deep sense, a projection of two-dimensional information. Not that the three dimensions are an illusion, but that the information specifying what's in them is fundamentally two-dimensional. What does this mean for our understanding of space and time? Some physicists believe space-time itself might be emergent, something that arises from more fundamental quantum mechanical ingredients. Mark van Ramsdonk showed in 2010 that reducing the entanglement between parts of a quantum system corresponds to pulling apart pieces of the dual spacetime. Less entanglement means more distance. No entanglement means space pinches off into disconnected pieces. Entanglement, in this picture, is the thread that holds space together. And black holes fit naturally into this framework. The event horizon is a surface where entanglement is maximized, where quantum connections between inside and outside are most intense. When the black hole evaporates, those entanglement threads are gradually transferred to the Hawking radiation. The fabric of the interior is slowly unraveled, its threads woven into the outgoing radiation. If this picture is correct, the evaporation of a black hole isn't just thermodynamic, it's topological, a reshaping of the quantum fabric of spacetime. The black hole doesn't just radiate away its mass, it radiates away its space. The interior geometry is gradually encoded into the external radiation and ceases to exist as a separate region. The information, the geometry, the very existence of the interior might be preserved in the radiation, encoded in a form we can't read, but that the laws of physics guarantee is there. This is what the latest research points toward. The tools being developed, quantum extremal surfaces, entanglement islands, the Ryu-Takayanagi formula, are all aimed at making this intuition precise. The disappearance of black holes is not a loss, it's a transformation. The most extreme gravitational phenomena, viewed through quantum information, are not destructive, they're creative. They take the information of everything that falls in and re-encode it into the radiation that flies out. Let's talk for a bit about something I find particularly captivating about this whole story, the human side. Because physics isn't done by equations on a blackboard, it's done by people. Messy, stubborn, brilliant, sometimes petty, often generous people who spend their lives trying to understand how reality works. Think about Hawking. When he made his famous calculation in 1974, he was already severely disabled by motor neuron disease. He could barely move. He communicated with great difficulty. And yet, he produced one of the most important pieces of theoretical physics of the 20th century. By thinking, by sitting in his wheelchair and working through the mathematics in his head, because writing was becoming impossible. Hawking's calculation wasn't the result of a big research program. It was one person thinking deeply about a question everyone else had either not asked or assumed was uninteresting. Before Hawking, most physicists thought quantum effects near a black hole would be negligible. He showed they weren't. That the marriage of quantum mechanics and curved spacetime produces radiation from nothing, temperature from geometry, the slow dissolution of the most permanent objects in the cosmos. Then there's Bekenstein, a graduate student proposing to his advisor that black holes have entropy. This was audacious. Hawking himself initially opposed it, and yet Bekenstein persisted, published his results, and stood behind them even when one of the most famous physicists in the world said he was wrong. And he was right. Or Chandrasekhar, 19 years old on a steamship, working out the fate of massive stars. Arriving in England with a revolutionary result, only to be publicly humiliated by Arthur Eddington, who simply couldn't accept the conclusion. Chandrasekhar spent decades under that cloud. It took until 1983 for his Nobel Prize. He was patient, he was right, and he lived to see his ideas vindicated. And Susskind, the combative Stanford professor, who couldn't let go of the idea that information must be preserved. For decades he developed new ideas, complementarity, holography, scrambling, all aimed at resolving the paradox without abandoning unitarity. For Susskind, this wasn't abstract. If information could be destroyed, physics itself was in trouble. What strikes me is how personal these stories are. These aren't just problems on a chalkboard. They're the life's work of people who cared deeply about getting the answer right. And that adventure continues. Right now, graduate students are working on aspects of this problem. Some will spend years on calculations that lead nowhere. Some will reshape the field. The story is still being written. Let me take you a little deeper into how Hawking radiation actually works, because the virtual particle picture I gave earlier, while useful as an intuition, isn't quite the full story. And the full story is, in many ways, even more interesting. The way most people learn about Hawking radiation is through the virtual particle pair picture. Particle and antiparticle pop into existence near the event horizon. One falls in, one escapes. The escaping one becomes real radiation. The one that fell in had negative energy, which reduces the black hole's mass. This picture is vivid and memorable, and Hawking himself used it in popular descriptions. But it's a simplification. What Hawking really showed is subtler and more profound. The real calculation involves the quantum vacuum, the ground state of the quantum fields that pervade all of space. And here's the key insight. The quantum vacuum is not the same for all observers. What one observer considers empty space can look different to another observer, depending on their motion and the gravitational field they're in. A particle is, fundamentally, an excitation of a quantum field above its ground state. But if two observers disagree about what the ground state is, they'll disagree about whether particles are present. This isn't just a technicality. It's a deep feature of quantum field theory. The most famous example is the Unruh effect, discovered by the Canadian physicist William Unruh in 1976. Unruh showed that an observer who is constantly accelerating through empty space, will perceive a thermal bath of particles where an inertial observer would see nothing. The harder you accelerate, the hotter the bath. The Unruh effect and Hawking radiation are deeply related. Many physicists think of them as two sides of the same coin. The event horizon of a black hole creates a situation analogous to constant acceleration. A stationary observer, hovering just outside the event horizon, has to accelerate enormously to avoid falling in. And just like an accelerating observer in flat spacetime, they perceive thermal radiation. What Hawking's calculation really shows is this: the quantum field modes near the event horizon of a freshly formed black hole are different from what they would be in flat spacetime. When you trace these modes forward in time, the state that was initially vacuum has evolved into a state containing particles, thermal radiation at the Hawking temperature. The formation of the black hole has transformed vacuum fluctuations into real radiation. This means Hawking radiation isn't just a thermal effect, like a hot rock cooling down. It's a geometric effect. The radiation is produced by the shape of space-time, by the fact that an event horizon exists. Any horizon should produce similar radiation, and indeed, in 1981, Unruh proposed that sound waves in a flowing fluid could mimic this behavior. If the fluid flows faster than the speed of sound, it creates a sonic horizon, a point of no return for sound waves, analogous to the event horizon. The quantum vacuum near this sonic horizon should produce thermal phonons, analogous to Hawking radiation. These analog black holes have been experimentally studied. In 2019, Jeff Steinhauer at the Technion in Israel reported observations in a Bose-Einstein condensate showing thermal radiation from a sonic horizon consistent with Hawking's prediction. While this doesn't directly confirm Hawking radiation from real black holes, it confirms the underlying physics. The mathematical structure is the same. The thermodynamics is the same. The universe really does turn horizons into heaters. Let's think about black holes in a different way now. Not as objects of terror, but as objects of extraordinary simplicity. Because one of the most remarkable things about black holes is how simple they are from the outside. The no-hair theorem says that a black hole is completely characterized by just three numbers: its mass, its electric charge, and its angular momentum. That's it. A black hole formed from a collapsing hydrogen star is, from the outside, identical to one formed from iron, or antimatter, or books and refrigerators. All the detailed information about composition, the arrangement of atoms, the temperature, the chemistry, is hidden behind the event horizon. John Wheeler summarized this by saying, "Black holes have no hair. They're bald, identical except for mass, charge, and spin, and yet Bekenstein and Hawking showed that black holes have enormous entropy, 10 to the 77 for a solar mass black hole. That means the number of distinct internal configurations is 10 to the power of 10 to the 77, an absurdly large number, and yet from outside, all those states look the same. Three numbers, perfectly smooth. So where are all those states? What are they? In ordinary thermodynamics, we know the microstates. They're the different arrangements of molecules. For black holes, we know how many microstates there are, but not what they correspond to. What are the microscopic degrees of freedom? What is being counted by the Bekenstein-Hawking entropy? This question has been the focus of remarkable work in string theory. In 1996, Andrew Strominger and Kumrun Vafa at Harvard constructed a specific type of black hole within string theory and counted its microstates exactly. The number matched the Bekenstein-Hawking entropy precisely. Not approximately, exactly. For the first time, there was a microscopic explanation of black hole entropy. The black hole in the string theory description, is a bound state of strings and higher dimensional branes, and the entropy counts distinct configurations that look the same from outside. The Strominger-Vafa black hole was a special case, supersymmetric, extremal, five-dimensional, not a real astrophysical black hole, but the exact matching was hugely encouraging, suggesting string theory captures something real about black holes' internal structure. This doesn't prove string theory correct. We lack experimental evidence. But the microstate counting is often cited as its strongest theoretical argument. The broader lesson is this: whatever the correct theory of quantum gravity turns out to be, it needs to explain black hole entropy. Any theory that can't reproduce the Bekenstein-Hawking formula is incomplete at best. Black hole thermodynamics has become a litmus test for quantum gravity, one of the few concrete tests we have for physics at the Planck scale. Let's shift gears and talk about something closer to home: the black hole at the center of our own galaxy. It's called Sagittarius A, and it sits about 26,000 light-years from Earth, with a mass of about 4 million suns. And it, too, is slowly disappearing. Now, slowly is doing enormous work in that sentence. Its Hawking temperature is about 10 to the minus 14th Kelvin, 100 trillionth of a degree, above absolute zero. Its evaporation time is on the order of 10 to the 87th years. If its life were a 24-hour day, the current age of the universe would correspond to the first few trillionths of a nanosecond after midnight. Right now, it's absorbing far more energy from the cosmic microwave background than it's losing through Hawking radiation. It's actually growing. But give it time. Eventually, the universe will cool to the point where even the feeble Hawking radiation exceeds the energy absorbed. And then, over eons that make the age of the universe look like a fleeting instant, it will begin to shrink. The great gravitational anchor at the heart of our galaxy will gradually, silently, dissolve into a faint mist of radiation. And here's a thought that connects this back to you, right now. The warmth from your blanket, that's thermal radiation. Photons emitted by atoms, carrying energy from warmer to cooler. Every object with a temperature radiates. Your blanket, your body, the sun, and yes, black holes. They all glow. The difference between your blanket and a black hole is one of scale, not of kind. The same physics, statistical mechanics, quantum field theory, thermodynamics, describes both. The universe is comprehensible. The same rules govern the mundane and the magnificent. Now, let me tell you about the final moments of a black hole's life. As it evaporates and shrinks, its temperature rises. Less mass means higher temperature, which means more radiation, which means faster mass loss. For most of its life, this acceleration is barely noticeable. But in the final stages, the process runs away. The black hole reaches a point where its temperature is extraordinarily high, temperatures that haven't existed since the first fractions of a second after the Big Bang. The Hawking radiation shifts from low-energy photons to high-energy particles of all kinds. And in the very last instant, the black hole releases whatever energy remains in a burst of high-energy radiation, comparable in energy to a large nuclear explosion, happening in a fraction of a second. Then silence. Where the black hole had been, nothing remains but a shell of radiation, expanding outward at the speed of light. Our current theories can describe the evaporation right up to where quantum gravitational effects dominate, but at that point, we lose predictive power. Does it disappear completely? Leave a remnant? Expose a naked singularity? We don't know. What we do know is that the final burst would be detectable. Astronomers have been looking for primordial black hole evaporation events, gamma-ray bursts from hypothetical small black holes formed in the early universe that would be reaching their final stages right about now. So far, none found. Either they don't exist in significant numbers, or our models need refinement. Both possibilities are scientifically interesting. I want to spend a while now on a topic that connects everything we've discussed, the quest for quantum gravity, because the disappearance of black holes is, more than anything, a signpost pointing toward the next great revolution in physics. General relativity describes gravity. Space-time is dynamic. Matter curves it, and that curvature tells matter how to move. The theory gives us orbits, gravitational waves, black holes, the expanding universe. It's been tested to extraordinary precision. Quantum mechanics describes everything else, the electromagnetic, weak, and strong forces, and all the particles that carry them. It predicts the outcomes of experiments to 10 decimal places. The magnetic moment of the electron, calculated via quantum electrodynamics and measured experimentally, agrees to more than 10 significant figures. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. Both theories are spectacularly successful, and they are fundamentally incompatible. General relativity treats spacetime as smooth and classical. Quantum mechanics treats spacetime as a fixed background on which quantum fields dance. When you try to apply both at once, when you try to quantize gravity, the mathematics breaks. Every calculation gives infinity. The standard tools of quantum field theory don't work for gravity. It's non-renormalizable. This is the central unsolved problem in theoretical physics. We need a theory that reduces to general relativity when gravity is strong, to quantum mechanics when quantum effects dominate, and gives something new where both matter, and where are both important simultaneously. Two places, the first moments of the Big Bang and the vicinity of black holes. Black holes are the laboratory for quantum gravity. The puzzles they present, the information paradox, the firewall problem, the singularity, Bekenstein-Hawking entropy, are all puzzles a theory of quantum gravity must solve. Every major approach is partly tested against its ability to address them. String theory can count black hole microstates and reproduce the Bekenstein-Hawking formula, Strominger and Vafa's 1996 landmark result. Loop quantum gravity, which treats space itself as quantized with discrete area quanta, also reproduces the formula for certain cases. The causal set program, developed by Raphael Sorkin and collaborators, derives it from causal structure alone. Different approaches, same answer. That convergence suggests the answer is robust. It doesn't depend on the specific theory, but on something more universal about the quantum structure of spacetime. The evaporation of black holes is the sharpest test, clearest puzzle, and most promising guide toward unifying gravity and quantum mechanics. When that theory is found, it will tell us what happens inside black holes, how information escapes, what the singularity really is. It will replace infinities and paradoxes with predictions, and it will transform our understanding of space, time, and reality itself. Here's a thought experiment I find particularly captivating. Imagine you could sit at a safe distance from a stellar black hole, 10 times the mass of our sun, and just watch. You have all the time in the universe. At first, you wouldn't see much. The black hole is invisible, no visible light, but you'd see its effects. If gas and dust are nearby, you'd see an accretion disk, matter spiraling inward, heated to millions of degrees, glowing in X-rays. Accretion disks around supermassive black holes, quasars, can outshine entire galaxies, pouring out more energy than 1 trillion suns, all powered by matter falling toward the event horizon. But let's say the accretion disk has dissipated. The black hole is isolated. You wait. If you had detectors sensitive enough, far beyond anything we can build, you would eventually detect a faint glow. Hawking radiation. Not visible light, but photons of such absurdly low energy that their wavelengths stretch tens of kilometers. A temperature of 6 billionths of a Kelvin. You're not seeing it with your eyes, but it's there. And if you had the incomprehensible patience to sit for 10 to the 68th years, you'd watch the black hole shrink, the glow brightening infinitesimally, the temperature rising by fractions, the event horizon contracting by fractions of an atom, the slowest death in the universe. At some point, the black hole would have shrunk to the size of a mountain. Its temperature would be in the billions of degrees. The radiation shifted from impossibly long radio waves to energetic gamma rays, and the process would be visibly accelerating. Then, in the final moments, a flash. Gamma rays and high-energy particles, as the black hole releases its remaining mass. A bright burst lasting a fraction of a second. Then silence. Darkness. Nothing remains but a shell of radiation, expanding outward at the speed of light, carrying, encoded in its quantum correlations, the information of everything the black hole ever consumed. The longest goodbye in the universe, followed by the shortest farewell. And here's what strikes me as beautiful. The Hawking radiation is a perfect black-body spectrum, the most democratic form of radiation. All frequencies, weighted by probability, governed entirely by temperature. When a black hole evaporates, it converts everything, stars, planets, light, into the most equitable distribution of energy possible. But underneath that uniform appearance, as we discussed, there are subtle correlations, quantum entanglements between particles emitted at different times. The black hole's final output is simultaneously the most uniform and the most complex signal in the universe, featureless at first glance, but containing a complete record of everything that ever crossed the event horizon. That's a fitting metaphor for physics itself. The surface is simple. The depths are astonishing. The universe rewards those who look closely, who keep asking, but why? Because the answers are always there, in layers deeper than you imagined. Let me tell you about one more idea that I find particularly captivating: entanglement islands. This came out of those 2019 calculations that derived the page curve from gravitational physics for the first time. The setup is this. A black hole has been evaporating for a while. Some radiation has already traveled far away. Now ask, what region of space-time contains the information about the early radiation? The naive answer is that the information is in the radiation itself. But the 2019 calculations revealed something unexpected. After the page time, that halfway point where entropy starts decreasing, the information about the early radiation is no longer entirely in the radiation. Part of it is inside the black hole, in a region behind the event horizon called an island. The information about radiation that already escaped is inside the black hole? It sounds impossible. The island is behind the event horizon, causally disconnected from the outside. But according to the quantum extremal surface calculations, this region is encoded in the external radiation. The island is owned by the radiation, not the black hole. It's as if the radiation has reached back behind the event horizon and claimed a piece of the interior. The entanglement between radiation and black hole creates a quantum connection transcending the classical causal structure. The island is inside geometrically, but connected to the outside quantum mechanically. And this means the information that appears trapped is actually accessible from outside, encoded in radiation through quantum entanglement, in a way that only becomes apparent after the page time. The island formula gives a precise rule showing the entropy follows the page curve, rising, peaking, declining to zero, information preserved, unitarity intact. The mechanism involves a deep interplay between geometry and quantum information nobody anticipated. I should be honest. These calculations use simplified models, often in lower-dimensional spacetimes. Whether they extend to our four-dimensional universe isn't yet clear, but the direction is remarkable. For the first time, gravitational calculations say information survives black hole evaporation. The tools are gravitational. The answer is quantum mechanical, and the bridge between them may be our first glimpse of what quantum gravity looks like. Every time we push deeper into black hole physics, the boundary between inside and outside proves more porous than expected. Hawking radiation lets energy leak out. Quantum entanglement lets information leak out. Islands let geometry leak out. The event horizon is not a wall, it's a membrane, selectively permeable. And maybe that's the ultimate lesson, that absolute barriers don't exist, that the universe is woven together by entanglement, by quantum correlations, by the deep structure of space-time. Even the most extreme environments can't fully sever those connections. I want to talk about one more thing before we wind down, something connecting black hole physics to quantum computing in a way I find particularly exciting. Physicists have realized that black holes are the fastest scramblers of information in the universe. When something falls in, the information gets mixed, entangled across all degrees of freedom, faster than any other physical system. The scrambling time for a stellar mass black hole is milliseconds. For Sagittarius A, a few hours. That fast. And every trace has been distributed throughout the black hole's quantum state, in a way impossible to localize. This property has deep connections to quantum chaos and computing. A system that scrambles quickly is performing incredibly complex quantum computation. The black hole processes its input so thoroughly that the output appears random unless you perform an equally complex computation to decode it. Hayden and Preskill showed in 2007 something remarkable about this scrambling. If you've already collected more than half the Hawking radiation, past the page time, then information about anything falling in afterward comes back out almost immediately. The next few photons, combined with everything collected, are enough to reconstruct what just fell in. A black hole past its page time is essentially leaking secrets. It can't keep one for more than milliseconds. Of course, extracting the information requires a quantum computer beyond anything conceivable. But it's there. Some physicists have proposed that a black hole's interior can be understood as a quantum error-correcting code, where infalling information is encoded redundantly across all degrees of freedom. The Hawking radiation is the decoding process. This connection between black holes and quantum error correction has been enormously influential, with techniques flowing in both directions. Quantum information theory helping physicists understand black holes, and black hole physics suggesting new approaches to building quantum computers. And here's the thread connecting everything. Black holes take matter, energy, light, information, and transform it all. They scramble it in the most complex cipher the universe can produce. Then, slowly, over timescales beyond imagination, they give it all back. Every Hawking photon is a tiny piece of the answer. Every quantum correlation is a thread that, fully assembled, would reveal everything consumed. The taking is temporary. The giving back is eternal. The total information content of the universe is the same before the black hole forms and after it evaporates. It's just been through the most intense transformation imaginable. And isn't that what the universe does? Transformation, not destruction. Change, not loss. The first law of thermodynamics says energy can't be destroyed, only converted. Unitarity says information can't be destroyed, only transformed. The universe is not a machine for making things vanish. It's a machine for rearranging things. And black holes are part of that rearrangement. The most extreme part, but part of it nonetheless. So, where does all of this leave us? We started tonight with a simple, striking idea. Black holes are disappearing. The most powerful gravitational objects in the universe, the things from which nothing can escape, are slowly, imperceptibly radiating away their mass and dissolving into the cosmos. And from that single idea, we've spiraled outward and inward. Through quantum vacuum fluctuations and the curvature of space-time, through the information paradox and the black hole war, through holography and entanglement islands and the quest for quantum gravity. And the deepest lesson, the one that emerges from every thread of this story, is that the universe does not lose, it transforms. The information that black holes consume is not destroyed. It's encrypted, scrambled, transformed into the most complex quantum state imaginable, and then slowly radiated back into the universe from which it came. The taking is temporary. The giving back is eternal. Now, I should be honest with you about what we don't know. We don't have a complete theory of quantum gravity. We don't know, in detail, how information escapes from a black hole. We don't know what happens at the singularity. We don't know whether the holographic principle applies to our actual universe. We don't know what the microscopic building blocks of space-time are. These are big unknowns, and some may remain open for decades more. Physics moves in deep time. Individual breakthroughs can happen suddenly, but the full understanding unfolds over generations. And that's more than okay. It's part of what makes physics so magnificent. The fact that the deepest questions about the nature of reality are still open means there is still adventure to be had. The story of black holes and information and quantum gravity is far from over. In some ways, it's just getting started. So as you lie there, perhaps already drifting toward sleep, I want you to hold on to one image, a black hole in the far, far future of the universe. Everything else is gone. The stars, the galaxies, the planets, the cosmic microwave background. The universe is dark and cold and vast beyond imagining. And there, in the emptiness, a supermassive black hole sits. It's been there for eons beyond counting. It was the gravitational heart of a galaxy that no longer exists, and this black hole is glowing, not with visible light, but with the faintest conceivable radiation, photons of such low energy that their wavelength is larger than the black hole itself. Hawking radiation, a temperature so close to absolute zero that it's barely distinguishable from nothingness. But it's there. The black hole is radiating. It's losing mass. Photon by photon, it's dissolving. And in that radiation, in the quantum correlations between photons separated by billions of years of emission, there is a record. A complete, incomprehensibly scrambled record of everything the black hole ever consumed. Every star, every planet, every photon of light that ever crossed its event horizon, all of it encoded in the faintest possible glow, slowly being released back into the universe from which it came. The black hole is not hoarding, it's returning, slowly, patiently, over a timescale that makes the age of the universe look like a heartbeat. And the universe, at its most fundamental level, preserves everything. Even the most extreme gravitational environment, the most absolute seeming barrier, the most final seeming darkness, cannot permanently erase a single quantum of information. The black holes are disappearing, and they're taking everything with them, but only for a while, because everything they take, they give back. Everything they consume, they radiate. Everything they swallow, they return, transformed and scattered, but fundamentally intact. So as you drift off tonight, carry that with you. The darkness is not empty. The silence is not final. Even the most absolute seeming endings are really just transformations in disguise. And somewhere out there, right now, a black hole is slowly, patiently, photon by photon, returning the light to the dark. Sleep well.